Welcome back class to our course on mechanical behavior of materials part 2. So in the last lecture we discussed about the variation of stress intensity factor for different configurations or geometries of the plate. Okay. So today we will discuss about the concept of fracture toughness, which is one of the most important parameter we use for design purpose. Okay. So let's proceed. So we will talk about fracture toughness. Okay. So now suppose I have a plate and the track is there. So let's talk about, say we have SENT plate just for understanding. Okay. So suppose the track length was A1 and it was under an applied stress of say sigma. Okay. Now due to some circumstances, suppose the track length increases from A1 to A2. Suppose we are doing fatigue, okay, at the constant amplitude. We'll discuss about fatigue later on. Okay. And now it becomes A2. So the total track length now becomes A1 plus A2, which is greater than A1, right? And if you remember, the formula for K was Y sigma root pi A. Okay. And for SENT, it is Y is equal to 1.12. And if I take CCT, Y will become 1 for infinite plate. Okay. So if the track length is increasing, so this A, if it increases, sigma is constant, so K is also going to increase, right? Okay. Similarly, if we keep the A fixed and increase sigma, K is also going to increase. Okay. So K can increase either by increasing sigma and keeping A fixed, or by increasing A keeping sigma fixed. Okay. So if we consider this particular configuration and the track is growing, say with respect to time or number of cycles, at some point of time, K is going to reach to a particular value where the material is going to fail, isn't it? Right? So that particular value will be called as fracture toughness. Okay. So again, if we increase the track length and keep sigma fixed, K is going to increase and it is going to attain a particular value where the material is going to fail, and that particular value is fracture toughness. Okay. So as soon as K becomes Kc. So now I am introducing a term called Kc. The material is going to fail. Okay. And this Kc here is called critical stress intensity factor. Okay. So as soon as K1 becomes equal to as soon as K1 becomes equal to Kc, right, your material is going to fail. So that is the critical condition, isn't it? Because material is failing at that particular value of K. So we call it as critical stress intensity factor. Okay. So Kc we can define as stress intensity factor at which the crack grows in unstable manner. Okay, so that is Kc. So this means if I have now Kc, so now let me write this particular equation in terms of Kc. Okay, previously it was only K1, right? So Kc will have a combination of sigma c and root pi Ac. Okay, so either sigma c has to reach or Ac has to reach so that the stress intensity factor becomes equal to the critical stress intensity factor. So if one of two are reaching the value of sigma c and Ac, the material is going to fail. Either load, or in this case a sigma c, because load can be converted to sigma c, okay, or A, which is Ac in this case, have attained, okay, or sigma has reached to sigma c or A has reached to Ac, okay. So either load sigma c or Ac have attained, okay, that means sigma has reached to sigma c and A has reached to Ac, okay, and as soon as that happens, the stress intensity factor reaches to a value of Kc and material fails. Okay. Kc, okay. So now I am introducing the term called plane strain fracture toughness, which is K1C. Okay. So in this course, I am going to make difference between Kc and K1C. Okay. Different books will have different terminology, but in this course, we will have Kc, which is stress intensity factor. This is, I have already mentioned, critical stress intensity factor. And K1C in this course, we will use as plane strain fracture toughness, okay, or critical stress intensity factor in plane strain condition. Okay, so remember the difference between Kc and K1C, and you will see eventually what is the difference between Kc and K1C when I will show you a plot. Okay, so now we can write K1C same as Kc. Okay, y sigma c root pi Ac, but here K1C is in plane strain condition. Okay, now this K1C is a material constant, and if we face the environment, it is not going to change. Okay, so it depends upon the material and environment. So K1C varies with material and environment. So if you fix the material and environment, K1C will remain fixed. Okay. Now, when we design, we can design based on either the stress or we can design based on the flaw size in the material. Okay. So we can have two conditions. One is maximum flaw size dictates design stress. So what does it mean? That we are keeping flaw size fixed. That means we have done say NDT and we know what is the maximum flaw size there. Okay, and based on that, the design stress should be calculated. So K1C is Y sigma C root pi AC. So sigma design we can write as K1C divided by Y root pi A max. And ideally it should be less than this particular value. Okay. So if we know what is the maximum flaw size in a given plate, we know what is K1C, that value is given. So based on that, we can calculate what is the stress requirement. And remember, Amax, now we are denoting that as say AC and K1C is known. So we are actually calculating sigma C. So we have to keep the stress value less than sigma C so that your material doesn't fracture. Right? If you are higher than sigma C or sigma design here, then your material is going to fail. So if I plot sigma design versus Amax. So for a particular Amax, we are going to obtain a particular sigma design value, right? A fixed design value. Say for this Amax, we got sigma design value of this. For Amax of this particular value, we got something like this and so on. So we can obtain a plot like this. Okay. And if we are above this line, so if we are in this particular region, the material is going to fail. Okay. And if we are below this, if we are here, safe region. Okay. So given a plate, we know what is K1C and we have done NDT. We know what is the maximum flaw size. We can calculate what is sigma. Okay. And if you are above that particular value, material will fail. And if you are below this, material is not going to fail. So this is what this plot shows. Now we can do the opposite where we know what is the sigma. So we can calculate what is the maximum allowable flaw size in the material. Okay. So design stress dictates maximum flaw size. Okay, so sigma is known. We are calculating what could be the maximum flaw size so that it doesn't fail. Okay. So again, K1C Y sigma root pi A max. And let's say this is now design. Okay. So now we can write this equation as A max equal to 1 by pi K1C by sigma design square. Okay. And if the material doesn't fail, then in that particular condition, Amax has to be less than 1 by pi K1C Y sigma design whole square. So if we plot this again, like we did last time, so here we have now Amax, and then the bottom will be sigma design. So for a particular sigma design, say this particular design, we are now getting a max value here. Similarly, for this particular design, we are getting this and so on. So we can actually get a plot like this. Okay. Now again, which region is safe and which region is unsafe? So same as the last time, the top part here, if we are in this particular regime, here material will fail. And the bottom region, material is safe or material will not fail. Okay. So we can use K1C or plane strain fracture toughness data to calculate either sigma design or the allowable maximum flaw size in the material so that it doesn't fail. So, plane strain fracture toughness is being used for designing purpose a lot. Okay, that is why I already mentioned that this is one of the most important parameters we use. Okay. So why did I distinguish between KC and K1C here? So let's understand that. You already know about the plane stress and plane strain we have discussed. So typically, if we have a plate and if it is very, very thin, for all practical purpose, we assume that it is in plane stress condition. And if the material plate is thick, it is in plane strain condition. Okay. Now, if I take a particular plate, we can also say that the surface, so suppose this is the plate here, the surface, both the surfaces, this side and this side, that will be in plane stress condition. Okay. And as we move inside, it is going to be under plane strain condition. Okay. And if that is the case, your plastic zone size is also going to change and the crack growth behavior is also going to change. Okay, I will show you now the variation in plastic zone size and the crack growth behavior we will discuss when we talk about the fracture mechanisms. Okay. So we are now talking about variation of fracture toughness with thickness. Okay, so depending upon the plate thickness, your material fracture toughness is going to change. And at a particular thickness value, below which your material is going to be under plane strain condition. And that's when we call it K1C. Okay. So if we have a crack, so suppose this was my plate. So it's like a crack. Okay, I'm showing the crack in 3 dimensions. Okay. So this is your crack here. And this is the crack's front. Crack front means the front part here. Okay. So this part here is my crack front. Okay. So now if I see the variation of stress through the thickness, right? This particular, now if I just let me draw surfaces here. So these are my surfaces of the plate, right? So this is under plane stress. The other surface is under plane stress. And inside we are going to have plane strain. Correct? Okay. Because on the surface it is free. So sigma z, right? Or inside the plane stress is going to be 0. Similarly, on the other surface it is going to be 0. So both the surfaces are under plane stress, and inside you are going to have all the three stresses. So you are going to have plane strain condition, right? And then remember we had discussed in the plane stress condition it is biaxial, and in the plane strain condition it is triaxial mode. Okay. So now if I plot sigma z, which is through the thickness, or sigma 3 with respect to distance from the center of the plate. Okay. So this is 0. So this is the mid point. So we are say here. Huh? So this is your midpoint. And then we are moving from midpoint towards the surface. So here we have distance from surface. Okay. If your plate thickness is B, so what will be the distance from the midpoint towards the surface? That will be B by 2. So here, right? So this becomes the surface. So that is under plane stress condition. So sigma z is 0. Okay. And as we move inside, you're going to see plane strain condition, right? So we can draw something like this. The variation of sigma z. Something like this. Okay. Where here you have plane strain condition. Okay. So you have very high triaxiality. At B by 2 position, which is the surface, you have plane stress condition, which is in biaxial mode. Here discussed, right? Plane stress is also biaxial, and it makes sense because sigma is 0. So you have only two stresses. And in between, you are going to have again triaxial stresses, but it will be slightly less. So lower triaxiality we can say. Okay. So your sigma z is varying like this through the thickness, where it is going to be 0 at the surface, and then it will reach to a maximum which is corresponding to the plane strain condition. And the same thing will happen on the other side of the midpoint. Okay, so it will go like this, and then it will go down to 0 value on the other side of the midpoint of the plate. Okay. Now what will be the plastic zone? So again, plastic zone is higher in which condition? It is higher in the plane stress condition, and then it is the lower in the plane strain condition, right? So if I again see the variation of plastic zone size from the surface to the other surface, it is going to be the highest at the surface, then it will decrease, right? And then again it will increase, and then it will be again highest on the other surface, because both the surfaces are in plane stress condition. Okay, so let me plot that. So if you have a crack, okay, so you are going to see a larger plastic zone at one side of the surface, okay, and then it is going to decrease. Okay, and then it is again going to increase. to other surface. Okay, so this is your one surface here. This one is your another surface of the plate, and both the surfaces are under plane stress condition. So your plastic zone size is larger. This is also under plane stress condition. Okay, and as you move down, your triaxiality is going to increase. Okay, and that means your plastic zone size is going to decrease. So here you are going to have plane strain condition, very high triaxiality. Okay, so you have smaller plastic zone size. So this is how your plastic zone size varies from plane stress to plane strain condition. Okay, throughout the thickness. And if I just see the projection of it, is going to look like this, where you have the smaller version and then the larger one. So I'm seeing the projection. Okay, so this will correspond to plane stress on both the surfaces, and this will be inside, which is plane strain. Okay, so this is how the plastic zone size changes through the thickness. Right? Now this will lead to the variation of fracture toughness values also through the thickness. Okay, there is one more reason to it, the variation of fracture toughness with thickness, and I will discuss that when we will talk about the fracture mechanisms. Okay, but for now, this is one of the reasons, because of the variation of plastic zone size, your fracture toughness is also going to vary through the thickness. Okay, not through the thickness, vary with respect to the thickness. Okay, so if you have very thin material, then your material is under plane stress condition, so your fracture toughness is going to be higher, right? Because your plastic zone size is also higher, right? And if you increase the material thickness, increase the material thickness, you are going to have more amount of or more magnitude of plane strain condition. Okay, and your fracture toughness is going to decrease, and eventually you are going to reach to a particular thickness value, after which it is predominantly under plane strain condition and not in plane stress condition. Okay, so at that particular point, your fracture toughness value remains constant. So let me plot it so that you can understand it better. So it is going to vary something like this. Okay, so this is your Kc. Now this is critical stress intensity factor. Okay, or we can call it also fracture toughness, right? But not plane strain fracture toughness. And this particular point here, this is corresponding to K1C, which is plane strain fracture toughness. And now this becomes material property. You can see with even at higher thickness, so B is here. Okay, and KC varies along y-axis. So if we are having B higher than a particular value, it doesn't change with thickness of the plate and it becomes the material property. So we call it plane strain fracture toughness, and it is a material property. Okay, and if the thickness is lower than this, value, so this is, I would say, let's say critical thickness. Okay, so if the thickness of the plate is lower than the critical thickness of the plate, then it is the fracture toughness or critical stress intensity factor is changing, right? It is increasing as you reduce the thickness. So it is not constant because it is depending upon the thickness. So here you have plane stress condition. So your material is very thin, so that your material is predominantly under plane stress condition. Here it is plane stress condition, sorry, plane strain condition. The material is sufficiently thick so that it is predominantly plane strain condition, and in between you are going to have contribution from both plane stress and plane strain condition, right? So you are going to have mixed mode. Okay, so your Kc value changes with thickness, and after a particular value of thickness, it remains constant. That value is called K1C, plane strain fracture toughness, and that is a material property. Okay, so let me show you from one more schematic, right? So suppose I have a thickness of the plate like this, then I am increasing the thickness of the plate like this, and then I am making it, very, very large. So here the surface in both the cases, so let's say this is plate A, plate B, and plate C. Okay. So in plate A, if you see, both the surfaces are under plane stress, and as you go inside, you can have plane strain also. But if it is very, very thin, it is predominantly plane stress. In plate B, both the surfaces are again under plane stress, and as you move inside, you are going to see plane strain condition. Okay. Now come to C, you also have plane stress condition at the surface, but it is so thick that it is predominantly under plane strain condition and not a combination, right? So this will fall, I would say, looking at the schematic, and if it should be greater than BC, if I say, BC is critical thickness of the plate. Okay, so depending upon the thickness of the plate, your fracture toughness is going to vary. And we are going to eventually talk about the determination of fracture toughness from ASTM standard, and there is a criteria for thickness of the material to be used to which can satisfy the condition of plane strain. Okay, we'll discuss that. So now let's solve some problems so that you can understand how to determine the stress intensity factor, etc. Okay. So let's solve one or two problems related to that. So the question one is, find critical crack length for different configuration or geometries when K1C is given. So is the fixed material, okay, and environment is also fixed. What we are doing, we are just changing the geometry of the plate. Okay? So K1C is fixed because your material is fixed. Okay? Applied stress is 100 MPa. And K1C, it is fixed and it is given as 50 MPa root meter. So we have been given two values. K1C is given and applied stress is given. So we need to calculate what is the critical crack length. So we have three configuration. Okay, so the first one is what we have been using for a long time now. So this is, say, A, plate A, where you have central through crack. Okay, so this is CCT and it is an infinite plate. Okay, so here your crack length is 2A. Now second is semi-infinite SENT. Okay. So crack length here is A. So this is condition 2. And the last one is penny shaped crack. This is new to you. So I will just draw. Again, infinite plate. So if you remember, I am drawing zigzag line, and I have already told that this in this course, this belongs to the infinite plate. Okay? So this is a 2D crack like this. Okay? And the crack length is denoted like A here. So this is penny shaped. Okay, again infinite. This is semi-infinite. And this is also infinite. Okay, so we have these three conditions, these three configurations. So we have to calculate what is the critical crack length. Okay, and you will see that depending upon the configuration, the crack length is going to change, the critical crack length, although we have fixed the stress and K1C. Okay, so it depends upon the configuration of the plate also. So here K1C is Y sigma C root pi AC. So Y for CCT it is infinite, so Y will be 1. For SENT again K1C we can write Y. So this is a general equation. And Y for semi-infinite SENT is 1.12. Okay. And for penny shape, let me write down. It will be 2 by pi sigma C root pi AC. Okay. So we know what is the value of K1C. So if I just see the first equation, we know what is K1C. We have been given sigma applied stress here. Okay. So we have to calculate what is A in all the cases. Okay. So let's do one by one. So plate A, which is CCT. So K1C is Y sigma root pi A, and K1C is given as 50. Okay. Y is 1. Sigma is 100 MPa root pi AC. Okay. So now you know all the values. You have to calculate what is the value of AC, and AC will be coming out to be 79.6 millimeter. Okay. But remember, this was in, this is CCT, right? So the crack length is not A, it is 2A. So we have to calculate what is 2AC, and it will come out to be 159.2 millimeter. You can calculate. Okay. Please be very careful with the unit. See, K1C is MPa root meter. And A here, whatever you will calculate in this particular equation will come out to be in meter. You have to convert it to millimeter. Similarly, if I give you the value of A in millimeter and you are using K1C in MPa root meter, first you have to convert A in meter. Okay. So that don't make that mistake. Okay. So just check the unit of A, sigma and K1C. It should be of same unit. Okay. If a K1C is MPa root meter, A should be in meter. So you have to convert if it is given in millimeter. Now plate B, which is SENT, K1C Y sigma root pi A in 50, Y is 1.12, sigma is 100 root pi AC. Okay, and if you calculate, AC will come out to be 63.4 millimeter. So here we will just use AC because we don't need to convert it to 2 because we in SENT we use A only. Okay. Now plate C, which is penny shaped, K1C is 2 by pi sigma C root pi AC and applied stress space. So I'll just remove C here. So K1C is 50, 2 by pi into 100. So we can calculate what is AC, and AC will come out to be 196 millimeter. Okay. So you have three configuration. Applied stress is same, material is same, so K1C is fixed. So applied stress is same, but you see the critical crack length, right? Or the maximum allowable crack length or flaw size in the given plate is varying. It is the lowest in SENT and the highest in penny shaped crack. That means SENT is more dangerous, right? Because the AC value is smaller. So it can allow very small crack length as compared to CCT and penny shaped, right? So depending upon the configuration, your maximum allowable crack size changes. And vice versa also. If we face the crack length, the maximum allowable design stress will also change, right? The plot, if you remember. Okay. So overall, the above problem provides which type of crack or configuration, I would say. Configuration would be more dangerous when other parameters. And what are the other parameters here? Sigma and K1C are fixed. Okay. So from this problem, we understand the effect of configuration, okay, or geometry of the plate. So now let's solve another problem where we will understand the effect of crack length or A by W. So question 2, for a given material, so material is fixed, that means K1C is going to be fixed. K1C is 50 MPa root meter. Okay. Width of the plate is 30 centimeter. Okay. Central crack or through thickness crack this is 3 millimeter. Okay. So we have a plate of thickness, not thickness, width of 30 centimeter. So this is given, K1C is given 50 MPa root meter. Okay. And you have a very small crack here, 3 millimeter. Again, not up to the scale, but you can understand. Okay. So the plate is under applied stress sigma, and we have to figure out what is the maximum allowable sigma or design stress. Okay? What is the maximum allowable stress Okay. So if I have this plate, what is the maximum allowable stress? Okay. So we know K1C. So let's solve. So this is CCT specimen, right? Now this is not infinite. So you cannot take y directly equal to 1, isn't it? But for a particular case, if you can calculate what is A by W, and if it is very, very small, for all practical purpose, you can take y is equal to 1, and you will see this now. Okay. So let's solve assuming that y is not equal to 1. We don't know anything, and then we know the expression, we are solving the problem. Okay. So K1C is phi sigma root I. A is given, K1C is given, we have to calculate y and sigma. Y is not given, it's not equal to 1. So if you remember 2W here, right? You remember what we discussed for CCT, we take width as 2W. So 2W is given as 30 centimeter and 2A is given as 3 millimeter. Okay. And we also know for CCT, y is 2f A by W root W by I. See the last lecture. Okay. So from here, this particular equation, so let me write down equation 1 and equation 2. So from equation 2, we can find out what is the value of y. Okay. So to do that, we need to know what is FA by W. And for CCT, FA by W is given as pi A by 4W sec of pi A by W 2W and then 1 minus 0.025 A by W square plus 0.06 A by W 4. We know A, we know W, so we know what is A by W, right? So you can calculate and this will come out to be 0.088. Okay. Now use equation 2 and figure out what is y. So from equation 2, we can calculate what is y and it will come out to be 0.99297. Okay. Now see it's 0.99297. It is very nearly equal to 1 for all practical purpose, right? And if you see A by W here also, A is what? 1.5 millimeter and W is 15 centimeter. Okay. So A by W will be 0.01, which is very, very small as compared to 1. So for all practical purpose, although we can calculate y, but it is nearly equal to 1. So we'll just take it as 1. And then we can solve equation number 1. So from equation 1, K1C is equal to y sigma root pi A. K1C is 50, y is 1, sigma and then root pi A. So if you calculate sigma, it will come out to be 728 MPa. Okay, so this is a condition where for all practical purpose, we are assuming that A by W is very less, which is 0.01. So y is approximately equal to 1. Now let's increase the crack length. Let's fix the width of 30 centimeter and increase the crack length and see what happens to value of y. Okay? And then sigma also. So previously it was 3 millimeter crack length. Now let's assume the crack length has increased. And now this becomes 3 centimeter instead of 3 millimeter. So 3 centimeter, this is 2A. equal to 3 centimeter. So now you have a plate of 30 centimeter. Okay. And then crack length, again not up to the scale, of 3 centimeter. And then you have stress here. So you have to calculate sigma, right? So we are just increasing the crack length from 3 millimeter to 3 centimeter. And let's see now what happens. So here 2a by 2w is a by w, or this will come out to be 0.1. Previously it was 0.01, right? We can calculate again f a by w. Okay, and if you do that, this will come out to be 0.2819. And then we can calculate y from 2fa by w root w by pi a. Okay, so y will come out to be 1.0059. Okay, again very near to the value of 1. And if you use this value of y, sigma will come out to be. Now let's see condition C. Now suppose crack length has increased to 10 centimeter. So 2a equal to 10 centimeter. Okay. So a by w is 1 by 3, which is 0.33. Now it is not very less than 1. So let's calculate what is f a by w. So you have to use this formula for f a by w. Okay. So if you use that formula expression, f a by w will come out to be 0.545. Okay. And now we know the expression for y. So let's use that. So y is 2fa by w root w by pi a. And if we calculate, y will come out to be 1.0707. And sigma will be approximately. Okay. So see how it is decreasing. The maximum allowable stress is decreasing as you are increasing the crack length. Okay. So we are fixing the K1C. So you can calculate what is the allowable stress with respect to different crack length. Okay. So that is problem 1. Second problem. Okay. So we have understood the concept of fracture toughness, how it varies with thickness. Okay. And I also mentioned that at particular point, the fracture toughness or critical stress intensity factor becomes equal to plane strain fracture toughness, which is the material property. Okay. So I will quickly tell you about the ASTM standard of plane strain fracture toughness measurement, and in the next lecture we will talk about how to determine plane strain fracture toughness. Okay. So plane strain fracture toughness. So K1C. Okay. So depending upon the material, I told K1C is going to vary. So the critical thickness at which Kc becomes K1C is not constant for all the material, and it changes. So let me show you one or two examples. So we have say 2 steel. So this is steel 1 and then another one steel 2. Okay, so Kc on the y-axis on both sides. So in the first tail, we are having values of say something like this and so on. And the second steel is not very tough, so it is smaller values, so 20, 30, 40, 50, 60 and so on. Okay. And the thickness here is 5, 10, 15, 20, 5, 30, 20, then 50, 25, and then I dot 50, then 75, and then 125. So not up to the scale. Initially it's small, and then there is a variation. So it is not up to the scale. So that's why I've given dot here. Okay. And here it is 5, 10, 15, 20, 25, and then again dot, and then we see 50. Okay. So this thickness on the x-axis, this is in millimeter, and again thickness here in millimeter. Okay. So we have two steels. So in the first steel, K1C is 120 MPa root meter. And in the second steel, K1C is 30 MPa root meter. Okay. So this is the cutoff now. So in one steel, we have K1C here, and another steel, it is okay. So in one steel, the steel one, your Kc is decreasing, and then finally it becomes constant at say 75 millimeter. So here BC will correspond to nearly about 75 millimeter. And here BC will correspond to the smaller section thickness, so something like this. Okay. So this is the variation of Kc, and here BC will correspond to nearly 15 millimeter. Okay, so we have two steels, different material, different composition. So K1C in the steel one is 120, and it is of the BC is higher thickness. Okay, so if you want to obtain K1C value, you have to have thickness of the specimen in this regime here in steel 1. In the second steel, K1C is smaller, and thickness is corresponding to K1C is also smaller, the critical thickness. So you have to have thickness of the specimen to conduct plane strain fracture toughness measurement in this particular regime. Okay, so in steel 2, the requirement of the thickness for fracture toughness measurement, plane strain fracture toughness measurement is smaller than steel 1. Okay, so depending upon the material, the thickness requirement for to conduct the plane strain fracture toughness measurement is different. And to measure the plane strain fracture toughness, we use ASTM standard, which is E399. Okay, and this is for plane strain fracture toughness measurement. Okay, and what does it say? It says the track extension resistance under conditions of crack tip plane strain in mode 1. So it is in opening mode. Okay, so mode 1 for slow rate of loading under predominantly linear elastic conditions. And negligible elastic zone. Okay, so this also means that it provides the measurement of crack extension resistance at the onset 2% or less of crack extension. Okay, so we will use ASTM standard, which is E399. Okay, and we'll use compact tension specimen for in E399. Okay, and when we talk about this ASTM standard, we will assume the linear LEFM condition to be valid. That means the plastic zone size is negligible or very, very small. It is under mode 1 condition. Okay, and it will provide the measurement of crack extension resistance corresponding to the crack extension of 2% or less. Okay, so in the next lecture, we will start discussing about how to measure plane strain fracture toughness using E339, 399 ASTM standard. Okay. Thank you. We'll meet next week.